Hello everyone, my name is James Boyce. I'm your STEM choice for the day, and today we're going to be talking about force and how it's everywhere, all around us, all the time. And no, I don't mean by your metachlorian count, I mean by physics. First, we need to ask ourselves a question. What is force? A force is an interaction that, when unopposed, will change the motion of an object. For example, this ball is at rest and will stay at rest until it is acted upon by another force. Now, it will stay here in this spot until something acts upon it. So if there's an earthquake or wind, it will move because I'm applying force to it. Force relates to Newton's second law of motion. Force equals mass times acceleration. The bigger you are, the harder you fall. Let's see what that looks like. Let's conduct a thought experiment. This is an experiment we're going to do in our head based on stuff we already know. Let's say I have a bowling ball that weighs 12 pounds. And let's say we push that bowling ball at 12 miles per hour. First, we need to move miles per hour into feet per second to calculate this correctly. 1 mile per hour is approximately 1.4 feet per second. So let's do that 12 times. That would be approximately 17.6 feet per second. Now that we know our acceleration, we can go back to our mass. So let's put that into the equation. Force equals 12 pounds times 17.6 feet per second. This will give us our force, which is measured in newtons, named after James Isaac Newton. The amount of force that bowling ball would have moving at 17.6 feet per second is approximately 29.9 newtons. That's a little more than enough to crush an egg. An egg needs only 25 newtons to crush it. But if it were to hit somebody in the head, 29 newtons isn't really that much. When you compare a human skull cracks at 2,300 newtons. That's almost 500 pounds of force. Now, in the case of the egg, if you place an egg in the palm of your hand and you squeeze it, it won't break. Go ahead, try breaking an egg in the palm of your hand by squeezing it. Get permission first, and I'll wait here. Welcome back. Did your egg break, or did it survive? Let's break down why. If it survived, hooray! That means the force you applied to the egg was distributed evenly across the entire egg, meaning it wouldn't crack or wouldn't break. And as long as you didn't apply more pressure than the egg could handle, because everything has a limit, it won't break. However, if your egg did break, here's why. The egg, again, like everything else, will always break along the path of least resistance. So when you crack an egg on the side of a bowl or you squeeze in your hand and it breaks, look at the shatter points where it cracks. Those were the weakest possible points it could have broken at. Now, if you squeezed it in your hand and it broke and you made a mess, make sure you clean it up first of all. Second of all, it cracked because force was applied unevenly to the egg. Again, take note. Whenever something breaks, it will always break along the path of least resistance. Check out the slow-mo footage here of glass shattering. Glass shatters at such a high speed, even high-speed cameras can't even catch all of it. All of these paths were the paths of least resistance. That's why it broke there. There are 4 types of force. We have weak, strong, gravity, and electromagnetic. Let's take a look at how some of these forces work. We're going to observe Adam shoot some basketballs. Let's approximate that the basketball weighs 600 grams. In pounds, that's about 1.3 pounds. Adam needs to apply force that is greater than 1.3 pounds to move the ball. Now, as he's shooting the ball, the more force he puts behind it, the farther it goes. Now, why doesn't he make a perfect shot every time? Well, there are other factors at play such as gravity and air resistance. As the ball is going through the air, it's pushing air out of the way and is losing energy by doing it. And it's being pulled by gravity. Whenever a ball is shot, it moves in an arc. As the ball is moving through the air, it's losing the energy applied by the force Adam exerted. And gravity is also pulling it down. In the first half of the arc, it still has a push force behind it, but as it nears the middle of the arc, it loses some of that energy and doesn't have enough to overcome gravity and starts being pulled down, finishing the arc. The next time you go out and you play sports or you're playing a game, try to break down all the push and pull forces that are at work there. Are you pushing on something to make it move? Or are you pulling on something to drag it towards you? Think about the forces at work. As an example, if you do tug of war, okay? If you do tug of war with someone or even a pet, if you're both pulling that rope at 20 pounds, the rope's gonna stay in the middle. But if someone starts pulling the rope with more force than you are or the other team is, then they start to pull it that direction. Tug of war is a perfect example on how forces work. Consider things like gravity and air resistance and the wind and the weight of the object. Consider those things when the next time you're throwing a football or shooting a basketball or hitting a golf ball or even throwing a frisbee. Use all the factors at play, not just as a thing to overcome, but to your advantage. Professionals take these into account every time they're playing sports. They take into account the push, the pull, everything to make their shot count. I've been James Boyce, your STEM choice for the day, and I will see you in the next lesson.